Okay, so this is the start of the second part of the course, and in this second part of the course we will discuss typical behavior and atypical behavior. So let's go back to the introduction of this course, and so we are interested in describing phenomena. And this description is possible when phenomena are described by few relevant variables. So, there is a general set of phenomena for which quantitative description is possible in terms of few relevant variables. And these, paradoxically, are phenomena that involve a very, very large number of variables. So take, for example, a gas, like the gas in this room. Well, this is composed of a number of molecules that is very, very large. It's of the order of Avogadro's number, which is 10 to the 23. Molecules, and so you have a system with these many degrees of freedom, which are the position and the velocities of each of the particles. So in principle you should need to integrate these many equations of motion, like Newton's equation. But what it turns out is that actually you can describe the macroscopic properties of this system in terms of rather simple, of very few variables, like, say, for example, the pressure, the temperature, the volume. And there are very, very generic laws that describes this system. So, for example, at a high temperature, you will you have let's say this is high temperature. You have the pressure times the volume is very well approximated by the number of particles times Boltzmann constant times T. And this is a type of law that applies to any gas at sufficiently large temperature. So it's a very universal type of phenomenon. And the reason why we have this type of laws has not much to do with physics, but it has a lot more to do with statistics and probability. Because essentially nothing prevents to the molecules of the gas in this room to just concentrate in a very, very small volume. And, but this will never happen, okay? Because the behavior which is described by this law is essentially the typical behavior we see with essentially probability which is essentially equal to 1. Okay? So much of the thing that we want to describe is how this typical behavior arises, and because it is a stochastic, it is a statistical phenomenon, because it has to do with probability, then we can understand how this typical behavior arises by just studying probability. Okay, so and as I told you, so this applies in general. It's not only something that applies to high temperature. If you lower the temperature, then you can have a very reasonable description of systems like real gas, where there is a liquid phase and a gas phase, or a vapor phase, let's say gas phase, which is separated by a phase transition, and here you have phase coexistence. And so this typical behavior in physics takes the forms of phases that are separated by phase transitions, and also at a particular point where these phases just merge and the distinction between the phases disappears, what we will see is that what you see in physics is that the physical properties of systems here are very universal, in the sense that they apply to systems as different as, say, a liquid gas phase transition, or a magnet, or a binary alloy. Okay, so there are these concepts of universality, typical behavior, phases and phase transitions, which are specific properties of that you discuss in statistical mechanics, that actually can be understood by just studying systems of many random variables. Okay, the properties of systems that are composed of many random variables. Okay, and so, but this is not only what we will learn does not only concern statistical mechanics or statistical physics, but it also has to do with information theory. So what is a typical problem in information theory? So the typical problem is how do you represent information in an optimal way. And by information I mean, for example, a text. Okay, you take a text or a message written in a certain language, and you ask yourself, how can I represent it optimally? And this means, for example, how much can I compress it as much as possible. So the idea is that, and this is what happens when you compress a file on your computer, that say you have in general a text, and you want to transform it into a strings of zeros and ones. Okay, and so what you want to do is to do this transformation in such a way that the length of this message, of these strings of zeros and ones, of bits, is as small as possible. Okay, so this is one of the typical problem in information theory, which is the one of compression. And if you think about this problem, then essentially, in order to do this task efficiently, then you have to understand what is the structure of the messages that you want to compress. Okay, because the more you understand what are the regularities inside your messages, the more you can exploit these regularities to achieve a smaller string or a higher compression. Okay, So, and these regularities actually have to do with understanding what are the typical properties of the text that you want to compress. So, what are the properties that arise as statistical regularities in the text that you want to compress? Okay, so there is another typical problem in information theory, which is the one of communication. And typically you have two persons, say Alice and Bob, and they want to exchange messages. And in order to do this, they use what is called a channel. Channel can be, for example, your mobile phone is a channel. Okay. So the problem is that this channel is affected by noise. So that whatever, imagine that the message that A wants to send to B is a string of zeros and ones, like this one. So the effect of the noise means that sometimes in transmission, one of these bits can be turned from 0 to 1, or some of the ones can be turned into 0. So there is no, so the message, if you just send a message, then B will receive a slightly different message. A message which is corrupted by noise. So in order to ensure that Bob can receive exactly the right message, then what you can do is to think a little bit about an inverse problem of this one. So to build in the messages that are sent some structure in such a way that the typical outcome of this structure plus noise will be something that will still allow B to decode the original message. Okay, so again, you are interested in typical behavior. You are interested in devising, in this case, a typical structure for your messages that can be resistant or robust to noise. And again, if you, of course, this how robust these messages are will depend on the noise. So if you have a certain noise level, and if you plot here some sort of efficiency, or say how much the message that B receives overlaps, so the probability that this message is equal to the message that A sent, then typically for when the noise is low, then this efficiency will be very high. But then if the noise gets beyond a certain threshold, then the message will be completely lost in transmission. Okay, in the sense that so now this behavior here is exactly equal to phase transition in physical systems. So it is, from the statistical point of view, it's exactly of the same nature. So when the noise is, so you can think of this as noise being equal to a sort of temperature. So when the temperature is low, then you can have, you are in a particular phase, which is the phase where you can recover your message. When the temperature is high, or when the noise is high, then you cannot. Now, there is a third subject that is clearly related to all these questions, which is statistical inference. So statistics and inference. And statistical inference deals with essentially the inverse problem with respect to these ones, because well, in statistical mechanics you have a model, you have a theoretical model, and you want to understand what is the behavior that this model predicts. And in statistics and statistical inference, instead you start from the behavior or the data that you observe, and you want to infer what is the model that underlies this phenomenon, or that what is the model that has generated this data. And when you think about, so the model that you want is the model that for which you can think the data as a typical outcome of the model, or as the most likely outcome of the model. So indeed in statistics, what you do is typically to maximize the likelihood. Okay? So for your best model, you want the data can be considered as a typical outcome from your model. And again, in statistical inference, you may also want to compare different models. So you want to compare different typical behaviors. And this is not so different from considering different phases of in either statistics, statistical physics, or in inference. So even here, we will see that statistical, say, phase transitions do emerge. And so, of course, we are also interested not only in typical behavior, but we are also interested in atypical behavior. So, first of all, because, say, if you think from the point of view of statistics, there is this famous saying by George Box that all models are wrong. So whatever is your data, there is never going to be a true model that has generated this data, because all models are wrong. This is some models. The next part of the sentence is that some models are useful. Okay, so all models are wrong means that anyhow your data will never be a typical realization of a model. So it will always be an atypical realization. So this means that whatever theory you have, then this theory may describe the data that you have, but it can also make predictions on things that you have not yet seen, okay, on phenomena that you have not yet seen. And then you can do experiments, and when you do the experiment, you will get new data. New data that you can use to check your theory. Okay. Now, typically, so if experimental data agrees with the predictions, then you would say that your theory is confirmed, and then essentially you learn that your theory is okay. But if your experimental data is different from the prediction of the theory, then this means that this experimental data is an atypical outcome of your theory. And then you should think about how should you modify your theory. You should go from this theory to a new theory in order to accommodate for this observation. And the way you want to do this is in such a way that the atypical behavior of this theory, which is represented by the data that you have seen, becomes a typical behavior under the new theory. Okay? So what we are interested in is to explain atypical behavior as the typical outcome of a modified theory. Okay? And or we want to understand how does atypical behavior or very rare fluctuations or very unexpected fluctuations occur in the most likely way or in the most typical way. Okay, and this is also what you are interested in statistical inference, also what you are interested in statistical mechanics. So, say for example, if you have a theory that describes your system at high temperature, then you would like to make a prediction on how it behaves at low temperature. And this, of course, the behavior at low temperature is very atypical with respect to the behavior at high temperature. So, but it can be retrieved from the behavior at high temperature if you think about how, if you have a way of describing atypical behavior as the most likely way in which it can occur. Okay. So this is more or less what we are going to discuss in the second part of the course. So typically we are going to consider always systems where the number of variables or the number of events that we considered is going to infinity, and we are going to focus on asymptotic behavior.